my name is Iskandar. I'm a developer advocate at Qiskit. So, like Jordan for Braket.
Indeed. So tell us just really briefly, what is the launch that we're talking about today?
Okay, so today we're talking about launch of Qiskit Braket provider, which we can talk about a little bit. So you probably know Qiskit. Qiskit is open source SDK to run with to work with quantum computers on a level of pulses, algorithms, and circuits. So we bring new provider to be able to enable Qiskit to run on a Braket devices.
Iskandar, can you break down more what is the actual Qiskit Braket provider and what people can actually do with it?
Okay, to do that, I should like a little bit introduce what the Qiskit suite is. So we have a suite of tools around Qiskit. It is a core module called Terra. It is all of necessary abstraction to run quantum computations like circuit, algorithms, operators, and etc. Then we have high-level modules like Qiskit Nature to run chemistry. Then we have a lower-level module on experiments, and we have what's so-called providers, which is a great segue to talk about what we have to talk about today. So providers, it's a set of abstractions that allow you to connect to any quantum hardware. So, and today we're going to be talking about Qiskit Braket provider, which is the set of classes that allow you to connect to AWS Braket hardware devices.
I think a lot of us would love to see this. Do you have a demo to show us?
Yeah, exactly. Let me bring up my screen. Let me know if you see it, and I can start.
Yes.
There we go.
Can you see the Jupyter Lab?
Yes.
Yep.
Awesome. So this is Jupyter Lab. It is running on Braket service, which is here in a notebook. Okay. As I said, that Qiskit Braket provider is the give you ability to run Qiskit programs on AWS hardware. So let me actually quickly go through this diagram and see and give you like high level of understanding which classes abstraction maps to which one from Qiskit to Braket. So in Braket we have devices, which is abstraction to talk to hardware devices on Braket, and task to run execution of specific quantum program. In Qiskit, we have almost the same naming, but a little bit different. So we have backend to which is the AKA device, and we have job AKA task. And we have to be careful here because job in Qiskit is a different thing that is job in Braket. So, and we have a high-level class, which is called provider, which gives you access to the backends. And with that, I will start my small demo. Little bit of agenda about this demo. So we're gonna go through how to access devices, Braket devices, then how to run a simple circuit like a bell state. Then we move to a little bit more bigger circuit, like some random circuit, and we talk about transpilation. Then we go through algorithms, and we finish with the hybrid jobs. I will try to do it in a very fast manner. So if you have any questions, I think all of the links to the presentation materials will be shared. So, okay, in order to start working with that, you have to install Qiskit Braket provider. I already did this, so I will not rerun this cell. Again, we just simply importing all of the necessary stuff for this demo, so which is not interesting. I think we should start with this cell. So one of the things that Qiskit Braket provider gives you is actual provider class, which exposes one of the methods called backends. And if you run it, this make a background call to the Braket service to fetch all of the information about underlying devices and all of their connectivity maps, basically all of the necessary information about devices architecture. So while it's running, okay, so we had it. So here you can see all of the available devices that are running right now that are supported by the provider at this point. So some Rigetti devices, INQ, Oxford Quantum, and simulators, of course. So again, you can, in this diagram at the top, there is also two different versions of the backend. One of them AWS Braket backend, and Second one is Braket local backend. It stands for Braket local backend, which comes with the Braket package. And we have wrapper for that too. So you can instantiate it like this. Or in order to access the cloud version of the actual devices, you can query them all, like here, like we did here. Or you can query for specific device, like for example, here I want to state vector simulator. So yep.
So awesome. Yes, very, very excited for this demo. It's really probably our most frequently requested feature on the Braket team, to have a Qiskit provider, a way to write their code in the familiar Qiskit framework and run on these Braket backend devices. One thing I wanted to flag is that when you see this list of providers on the Braket side, these are actually all different real quantum computers that are available to be accessed right now. And exactly, yeah, thanks to Scanner, he's showing the devices page on the AWS console right now. So we have a lot of different quantum computers that are available, and we are always adding more. We've already pre-announced another one that is going to be a Rydberg atom array. And so the fact that you can now access these gate-based quantum computers is pretty exciting.
Yeah, thank you. Yeah, it's actually really, really interesting. It's heavily requested feature from the community, as you can tell. Okay, we can move forward, and same thing. We can request for other devices like IonQ or Rigetti. Here it is, or we can do some queries. For example, to the backend method, you just pass statuses you want or types of devices you want, and you can do the query. So maybe for some reason you want to pick whatever device is available and run your programs on that. So next up will be Hello World example for all of the quantum computing is basically running the Bell state circuit. So here how you construct it. So this is the circuit itself. Then we can run it on one of the simulators that we instantiated above. In order to run it, you just have your backend class. You call method run with the circuit you provided. It should be done right now, and you can see the distribution. So because it's simulator, it gives you almost perfect simulation all of the times. So
Iskander, we've actually got a question from the chat, which is, I think, probably one that a lot of folks have. So really, what is the advantage to quantum computers? What are they expected to be good for?
Okay, first of all, there is some misunderstanding about quantum computers. People think that they will change, they will remove classical ones, which is not true. Future of computation is hybrid, which is classical and quantum. Classical computers is great for doing the things that we're doing right now, but quantum computers are very good in other things. For example, one of the area which will be very popular for quantum computing, and it's not stated by me, but all of the community, it is chemistry simulation. I think this is one of the most important fields that quantum computers will be applied to. So it's like material design, chemistry simulation, I don't know, protein folding problem, and etc. So and of course a lot of optimization problems. Yeah.
Thanks for giving us a little bit of an overview there. Also, just wanted to flag that when we talk about materials design, there are actually a lot of applications to verticals like automotive, manufacturing, power. There's, battery design for quantum chemistry, really vast amount of different industries that could potentially be impacted by the advent of full-scale quantum computers. And so right now we're in a pretty early stage of the technology. And so most of the work tends to be around proof of concepts and more theoretical algorithm design. And so one of the nice things about Amazon Braket is that you can essentially follow along with the development of quantum hardware and see exactly where the state of the art is for a variety of different quantum hardware approaches.
Exactly. okay, so we will move forward a little bit. So now we run the simple circuit. Let's run something more heavy. So it's just a random circuit function that Qiskit has is generate just a random function. And now it's a good time to talk about what we call transpilation. In a compiler's world, transpilation means like converting something from one domain to the same domain. So it's almost compilation, but within not changing domain. So in that case, transpilation is converting one circuit to another. So why do we need to do that? It's actually a good question. For example, you have your circuit, which has different number of gates, and you want to run it against some device, which might or might not be supporting those gates. So that's where this transpilation routine come in handy, because it looks at the coupling map or connectivity map of the device, noise factors, and etc. to optimize your circuit to run for this specific device. So here, what we're doing here, we're passing our randomly generated circuit to the IonQ device. So it will be transpiled specifically for IonQ device. So here what we get as output, which will be equivalent circuit to the entered one. And then we can again run it like we did before. Yeah, we have a job ID. I have another job ID of previously run job, which is on the same device. Let me show you. You can get the job status, and you again can plot the histogram of the results. So here is the results. Also, all of these jobs, which is in Qiskit they call jobs, but in Braket, again, just to remind you, they're called tasks. So if you switch to this tab in Braket, you will see all of these tasks listed here. So you can look through them through Qiskit or through Braket UI. Okay, let's switch to something even more abstract and high level, is algorithms. So Qiskit comes with the suite of different algorithms, and one of the most popular algorithms are variational algorithms or optimization algorithms. And one of them is VQE. So basically what you're doing here, you're trying to solve optimization problem. You have some variational form, which will be in form of two local circuit. And you have Ising Hamiltonian, which is this Hamiltonian. And what you're doing here, you're constructing the VQE class, which is our optimizer with this waveform, give it some optimizer to run on, and you can run it with to compute minimal eigenvalue of this Ising Hamiltonian. So if you run it,
quick for the folks in the audience who might not be familiar with this type of algorithm, basically the goal of VQE is to find the ground state of different types of molecules or chemistry Hamiltonians. And Hamiltonian is just a description of the energy of like a quantum system, or really any system. So VQE has a lot of passing back and forth between the quantum computer and the classical computer, essentially to try to find the best circuits, well, the best parameters for which gates to apply to the quantum circuit, which has the quantum chemistry Hamiltonian encoded on it, so that when you repeat this for multiple iterations, at the end of it, the output of the quantum circuit is the ground state of the chemistry Hamiltonian. And it's quite an important property, really, for any application that is around quantum chemistry and things like material science development. And even to some extent, you can encode these sorts of things with larger scale molecules as well.
Exactly. Yeah, that's true. Very important algorithm, and it's like go through for the chemistry application, at least at this point, which is, yeah. So as a result, you get all of your optimal parameters for your problem, and yeah, you get eigenstate, you can evaluate other auxiliary operators if you want, and so on and so forth. Yeah, so Jordan
I was just going to say, quick.
Yep.
We got a question here from
Mhm.
Glupland, and Glupland wants to understand if there's any commercial usage right now that you've seen or that can really accelerate the development of quantum computers. And
okay, yeah, that's a great question, and I think from at least what I can see outside of the scope of any provider, any company, at least if you go to the LinkedIn or whatever, you will see more and more position will be popping up in a big enterprises and companies in financial sector, in chemistry, in pharma, which requires you to know the quantum computation. So that's pretty much showcase that companies and industry are interested in that, and for sure once we get to the quantum advantage phase, it would be for sure like bubbling up a lot. So right now chemistry and finance, I guess those industries that we should be looking at, which will be the like power through for the quantum computing technology.
And while we're on the subject of answering chat questions, we've got one about cryptography. And this is definitely something that comes up a lot in articles about quantum computers, saying that it's going to break all internet encryption.
Yes,
so
right.
Would you like to talk a little bit about that?
Okay, yeah. So this famous scary story about breaking all of the encryption boils down to this Shor's algorithm, which was the great kickoff for the quantum computing field overall, because it makes everyone talking about quantum computation and how it will break and like steal all of our money. All of our money will be stolen. So that's a huge media factor for that. But in reality, to run Shor's algorithm is a great theoretical advancement. But in reality, to run it, you have to have like a perfect quantum computer with like thousands of perfect qubits, which is not achievable in I don't know nearest future. So that's why we're in a era which is called NISQ, so noisy intermediate quantum right now. So it's like far away ahead. Plus, right now there is a protocol that can protect you from the quantum decryption. So there are encryption protocols that can protect you from quantum decryption. So you might not be worried about that, but for cryptography field, quantum computers are actually very useful because of some specific properties that allow you to pass information without like eavesdropper in the middle. So that's the cool thing about quantum computer. But breaking your passwords, you shouldn't worry about that anytime soon.
Awesome, thanks. So actually, we're just about at time here, but I wanted to ask a little bit about how the Qiskit provider for Braket was actually developed. What was the process there?
Okay, sure. We at Qiskit we have what's so-called Qiskit mentorship program, and I was the one of the mentors on this program, and this provider was built as a part of this mentorship program with collaboration with Amazon Braket, of course. Thank you for that. And yeah, repository lives in a GitHub. I want to hugely thank my mentee David, who was the core developer of this provider. Yeah, so this was the open source collaborative effort from Qiskit, Braket, and general open source community. So I think it's great. So science should be open and available for everyone. And yeah, that's what we're doing. That's why we're doing it. It's truly open source.
Oh, Jordan, you're on mute.
Yep.
Oh, I am. Thank you so much for joining us, Iskander. It's great to have you.
Thank you. Thank you.